Okay, so let's continue from our last lecture where we started talking about this statistical functional B statistics. So before that, if you remember, we have talked about the asymptotics of sample quantiles. So far, to summarize what we have covered so far, we talked about central limit theorems, right? So that is a big class of asymptotic distributions for statistics. Essentially, as long as the statistic is some sort of average, then you should think about central limit theorem and its variant. Depending on whether the random variables in your average are IID, right? That's the standard version of central limit theorem, or they are independent but not identically distributed, then you need Limburg-Feller, or they're identically distributed but not independent, then you need to see whether they have some short range dependence. We call that M dependence. That means the dependence only happens if random variables are within M in range. So that's where you still have asymptotics. So beyond that, then we talk about extreme order statistics. That means you have the minimum, maximum, second minimum, second maximum. For these, we can also talk about their asymptotics. And moreover, we talk about sample quantiles, right? For sample quantile, everything starts from the results we get from uniform distribution order statistic, because any distribution can be transformed into a uniform distribution through its CDF function. And then for the order statistics of uniform random variables, we actually can, how to say, equivalent their distribution to the ratio, partial sum of IID exponential random variables over the total sum, right? So that ratio between 0 and 1 can actually follow the same distribution as the uniform order statistic. And therefore, from there, we leverage central limit theorem for that partial sum ratio to derive order statistic asymptotics. So that's the thing. So most important results were in the previous lectures. In particular, to have the asymptotics of sample quantiles, we need to, this is the fundamental result. Let me find this one. Um, Here, this is the thing. So if you look at this one, right? So basically, this is the pth odd quantiles order statistic. This is the pth quantile. This is the population quantile, right? Sample quantile, population quantile. So in the asymptotic variance, it depends on the probability for that quantile PQ, because you can imagine that if P is small or large, it means that the quantile is closer to the two ends, two extremes. So therefore, once it's closer to the two extremes, yeah, it has certain properties. So basically, there's one thing to consider, which is the position. What is the quantile about? Is it in the middle or is in the two extremes? Another thing, which is the denominator, that's very important to look at, is this density function. Is the density function at this quantile? Because if the density is large, you will expect to have more sample to support your estimation of this quantile, right? So then you can see larger density give a smaller variance. Yeah, so that's also reflected. So in this very classical example, example one, we talk about using the median instead of the mean to estimate the population mean, to estimate the mean from Gaussian, the mean of a Gaussian distribution. Because in the Gaussian distribution, the mu is both the population mean and population median. They're the same parameter. Then on the sample level, we could use sample median and sample mean. But this says that under this model, right, if your sample is indeed from this model, let me move myself away. If your sample is indeed from this normal distribution, then median is less efficient than the sample mean, because you can see that pi over 2 is greater than 1, right? So using sample mean to estimate mu, you have a smaller asymptotic variance. So, and this indicates something very important to think about: the efficiency of estimator and the possibility of model misspecification. So essentially, we're saying that when the model is correctly specified, sample mean is more efficient than sample median. But people also say sample median is more robust. Robust in the sense of what? In the sense of model misspecification. In particular, medians more robust to outliers, to the existence of outliers. That means if we have some extremely large values that are unlikely to come out of a normal distribution, because normal distribution is very light tail, right? You don't expect observations normally beyond like 2 sigma, right, around the mean, because that's already 95% of the probability. So you don't expect to have so many outliers. But if you do, then in your data, then that possibly indicates some model misspecification. But in this case, using the median to estimate the mu, and if you believe mu is still like the population median, right, then using the median is more robust because it's less affected by the outliers. So that's another thing to consider. So essentially, efficiency and robustness, they are kind of like the trade-off. Yeah, you cannot really have both. So that's why when we do real data modeling, that kind of trade-off is a very important consideration. How would you choose your model? How would you come up with a model, and how would you choose your estimator? Okay, that summarizes the previous stuff. Hopefully it's a very quick review. Now let's move on to this part, statistical functionals, which is, I would say, compared to what we covered previously, this part is more abstract, okay? Because we're talking about this mathematical notations, but we're not talking about some real examples. Specifically, you can think of statistical functionals as parameters that are functionals of the true CDF function. That's pretty much it. So essentially, we can have the CDF function value fc itself is a functional of f. And the quantile is a functional of f, right? You can go from the probability to its population quantile. And the mean and the variance is also a function, functionals of f. So these are all functionals. So the reason why it is beneficial to define the functional is because we can actually come up with a natural estimator. That is, if we want to estimate a parameter expressed as some functional of f, then we can just replace f by fn hat. And fn hat is this empirical CDF function. And we're doing this so-called plug-in technique. That is, by replacing f, plugging f with fn hat. You use the same functional, then the result is an estimator. Because fn hat as an empirical CDF just depends on your sample, nothing else. Because essentially, empirical CDF is obtained from a discrete distribution where you place probability mass of 1 over n to each of your data points, right? A sample of size n, then each value xi receives a point mass of 1 over n, and you get a discrete distribution. And this is the corresponding CDF function. Okay, and this is empirical CDF. So essentially, if you use this as an estimator of f, by plugging in, you can estimate T of f by this T of fn hat. That's the general idea. So based on this idea, and in the special case where this TF, this functional, is something called expectation functional. That is, we write it this way. So what does this mean? This means that y is a random variable following distribution f, CDF. And then if you apply some g function transformation to y, g of y, you take the expectation. This is defined as T of f. The functional is defined as this expectation. And this encompasses a large family of parameters, which can be written as some sort of expectation of a random variable subject to transformation g. And more broadly, right, not just one y, we can have n such y's. So y1 to ym can be m IID from distribution f. And this can allow you to define more functionals. So later I'll show you that if m is set to 2, you can use this type of expectation of g with some sort of g at y1 and y2 to define variance of f. If you just want to define mean of f, then you just need one copy of y, just expectation of f at y, right? So gy, if you say g to be identity function, then expectation of y is just the definition of a mean. So you can just depending on, you can say the order of your parameter, like mean is called first order, variance is called second order. Depending on the order, you need a corresponding number of IID copies, random variables from F to define expectation functional. So essentially, from now on, all the functionals we'll focus on are the expectation functionals. So basically this form, that's what we will focus on. So m copies from this F. So y1 to ym are IID from F. Okay, so now the question is, how do we do plug-in, right? So if this is your TF, then what is TF and hat? That's our next question. So in this case, you are going to get a distribution. So you're just trying to plug in. It will become this expectation under f n hat of g y1 to ym. Please note that y1 to ym are just, how to say, notations to indicate that they are random variables. They are IID random variables from whatever distribution I specify in the subscript of this expectation, right? So here y1 to ym are IID from f. Here y1 to ym are IID from f and hat. That's it. And what is f and hat? As I already said, f and hat is just a discrete distribution over the n values, n data points in my sample. So essentially, this means y1 to ym are IID sample with replacement from my sample, actually, from x1 to xm. That's because f and hat is specified based on the sample. So y1 to ym are just sample with replacement from these n things. And by having replacement, it means what? It means that we could get more than one IYI that is from the same original xi, right? So there could be repeats in my y1 to ym. Okay, so what I just said is the definition of the so-called V statistic. So this is V statistic, essentially. So this is a V statistic as an estimator of TF. Okay, and V is from a person's last name, von Mises. So that's why we have this V. Essentially, yeah, I already said this, right? So essentially, what we are getting is you are here, denoted by Vn. Sample with replacement, you consider all possibilities for each yi. Since each yi has n possibilities across m such yi's, the total number of possibilities is n to the power m. We enumerate all of them. That's it. That's the V statistic. Okay. And but there's a problem, like I mentioned. There are repeats, and because of that, the expectation of Vm may not be equal to Tf. So this is the problem. So look at the star. For m equals 1, the equation here contains some terms in which these sampled things are not all distinct. Hence, the expectation of Vn is not necessarily, that's the problem, expectation of Vn, which is expectation of T at Fn hat, is not necessarily expectation of T of F. That's the problem. Yeah, because of repeats. oh, sorry, it's not equal, sorry, it's not equal to T of F. We don't need expectation on this side, yeah, because there's no random variable. So one example we ended up with last lecture is this example. So this one, let m equals to 2 and g be this function. It can be shown that the functional TF, which is you just apply this g to the y1, y2 from this f. TF is expectation of f of absolute value y1 minus 2 is not linear in f. This is not the first, this is the first thing, but this is not the most important I want to say here. That is, I want to say the next one. Furthermore, given a random variable sample, x1 to xm from this f, since this is identically 0 if I1 equals to I2, right? So then when you calculate the Vn and you calculate expectation of Vn, here what's non-zero in Vn are only the terms where I1 and I2 are not equal, right? So therefore, how many terms you have there? It's actually n times n minus 1, right? You have to exclude the identical ones. So because you have only n times n minus 1 in the sum, and one n is canceled with the denominator, then you see what you get out of here is not exactly TF, but TF times this n minus 1 over n. So there is a finite sample bias. But you can say this bias will go away as n goes to infinity. So because of this bias, it's natural to think, can we propose an unbiased version? And because of this unbiased need, or the term unbiased, we have U statistic. So essentially, you can think about the V statistic to U statistic. The difference is for V statistic, you have sample with replacement. While for U statistic, you have sample without replacement. That's the biggest difference. So in your definition of the statistic. But when you have sample without replacement, you are not having this exactly, you are not having f n hat, the empirical CDF exactly. Because if you treat it as a distribution, the sample from it should have replacement, right? But if you're doing sample without replacement, then you're not actually doing the plugin. So Vn is the plugin, Un is not. Okay, so by having sample without replacement, essentially, when you consider all possible values for y1 to ym, you are considering a subset, m subset of x1 to xm, and there's no repeats with it. And how many possibilities are there? It's actually n choose m. And I'm summarizing all these combinations, okay? That's pretty much it. So this is the U statistic. So you now can see the whole idea is coming from the statistical functional formulation for parameters. And then we do plug in to, which is a natural way to get a V statistic. But then we realize that for expectation functionals, if the parameter need to have more than one IID random variables from F to define, right? Y1 to Ym, when M is bigger than 1, then just doing plugin will have this bias issue. And to debias, or to get an unbiased version, we came up with this U statistic. That's the whole idea. Now let's look at one concrete example to help you understand how U statistic has been used. Okay, example 2 here. Suppose that we have pair data x1, y1 to xn, yn. Let me try to remove this bar, this thing away. Okay, suppose we have pair data x1, y1 to xn, yn. Let zi equals to yi minus xi for all I. Assume that zi's are independent and identically distributed with distribution function this. Okay, this is the CDF function of zi we're interested in. And in this distribution, there is a key parameter theta. So suppose that we can write this zi's CDF function as f at z minus theta for some theta, where this f is the CDF function of a symmetric distribution around zero. So in other words, you are wondering whether the distribution of zi is centered at zero. Okay, if that's the question you're trying to ask. So whether you want to know theta as a shift and theta is the center, whether the theta as a center is zero or not. So in other words, with zi being centered at zero, what does it indicate? It indicates that yi and xi have the same mean. You're trying to answer this question because you're taking their difference. Because if yi has a bigger mean than xi, then zi's mean should be positive, right? Or if yi is less than xi, then in mean, then zi's mean should be negative. Okay, so let W1 to Wn be a permutation of Z1 to Zn such that you basically sorted Zi's by absolute value from the smallest to the largest, okay? And then you refer to the sorted ones as W1 to Wn. So they're just a permutation of Z1 to Zn, but order from smallest to largest in terms of absolute value. And here's the test, theta being 0 versus theta being greater than 0. So we are trying to answer the question I just said, whether y and xi have the same mean. And now we have this classical test called Wilcoxon signed rank test. So you know Wilcoxon has two versions. One is called Wilcoxon rank sum test. This is called Wilcoxon signed rank test. What's the difference? For Wilcoxon rank sum test, your two samples are not matched. You can have x1 to xn, y1 to ym. There's no correspondence. But Wilcoxon signed rank test have pair data, applies to pair data. So essentially x1, y1 is about same observation, right? About same thing you measure x1, y1. And then x and y is about same thing. So for this pair data test, Rn is written as the sum. J goes from 1 to n, J times indicator function, Wj being positive. So remember, Wj's have been ordered in absolute value, but we don't care about the sign. We're just ordering absolute value. So essentially, we are looking at each order and we record whether it's positive or negative, right? If it's positive, then indicator value is 1. And we add, sorry, here. If it's positive, indicator value is 1, we add its order to the sum. If it's not positive, say negative, then indicator value is 0. So this order is not added. So what would you imagine if this Zi has a symmetric distribution, or if Zi has mean 0? What does it mean? What I should say, when Zi has a symmetric distribution about 0, what would you expect about this would happen to the sum? We would expect that the positive values should be randomly scattered among W1 to Wn, right? We shouldn't expect that, oh, the first half of the Wi's are positive or the second half of Wi's are positive. That would not indicate a symmetric distribution. We should expect something even, right? That's the thing. Yes, so this partial sum will capture that. Okay, the partial sum. And another thing to bear in mind is that since we sorted the Wi's by absolute value, by this absolute value, it means that the sum of the two things will be positive only if and only if the later one, because Wj after Wi, only if Wj is positive, right? Because if Wj is negative, then the sum will be negative since it has a larger absolute value. So that's why this is a very smart thing. So essentially, you know that, okay, indicator Wj being positive, it means what? It means that adding Wj to everything before it, you will get a positive sum, right? So that's actually this. So essentially, you are adding I from 1 to j. So W1 plus Wj would be positive if Wj is positive. W2 plus Wj will be positive if Wj is positive. And finally, wj plus wj, two copies of itself, will be positive if it's positive. So that's why you have exactly j copies here. That's it. So therefore, you see, I can write this Rm now equivalently as a double sum. At first, inside the original sum, j still goes from 1 to n, j goes from 1 to n here. But this term, j times indicator w being 0, is now replaced by this sum from about I goes from 1 to j, okay, and with this. And now, that's what. Now, because here, when w and wj, essentially you're adding up every possible pairs, basically, right? J goes from 1 to n, I goes from 1 to j. So you're adding up all possible pairs. So the rank doesn't, or the order doesn't matter anymore because you're going through all pairs. Then you can just restore wi, wj to zi, zj. So zi, zj is the pre-sorted version. Okay. That's it. So then now you can see this is what? This is can be written as what? Can be written in terms of the G function form. So basically you want to just let you see that it is a U statistic thing. So U statistic only requires the pair to be not identical. So basically U statistic require I to be not equal to J. But here we do have a case where I is equal to j, right? I goes from 1 to j, so I could be equal to j. So that's why we separate that term out separately when I is equal to j. So essentially, I'm trying to rewrite this Rn as a U statistic plus something. But please note that in the U statistic, we need to divide the number of combinations and choose m. But Rn doesn't have that division, so we introduce the division here. So Rn divided by n choose 2 is two parts. One part is just un, right? When they are not equal. And another part is the identical ones, I equals to j. So we need only a single sum there. And for that, because I equals j is I from 1 to n, two copies of zi greater than 0. So it's equivalent to zi being 0. That's it. But for this term, it's actually not so important, because the sum is on the order of n, but the denominator is on the order of n squared. And choose 2 is n squared. So that's why you have this cancellation and you are left with the order of 1 over n, which will go down to 0, right? So that's why this Rn divided by n choose 2 is dominated by un, and un is the U statistic. And the reason I want to introduce this example is just because you can see for such a Wilcoxon signed rank statistic, if you want to derive its asymptotic distribution under the null hypothesis that theta being 0, you just need to know the asymptotic theory for UN. That's it. So because it's dominated by UN. So remember the term we introduced in the first class. This and this are asymptotically equivalent. Okay, if they're asymptotic equivalent, you can just obtain the asymptotic distribution for something easier and then apply that to something more complicated. Does that make sense? No. Okay, so let's continue here. So this is what I just said. Where UN is the U statistic corresponding to the expectation functional probability. Okay, so basically you see, this is the U statistic I'm having here. So this one is what? Let me just write it down so it's clearer. 1 over n choose 2. Sum I less than j. Okay. G, because it's indicator, zi plus zj is greater than 0. Then I can, since G is defined in this way, this is basically n choose 2, double sum I less than j, G, zi, zj, right? That's it. Okay. And zi, zj are both from, well, zi, zj are just my sample, basically. It's just my sample. And what does this estimate? You see, this is the U statistic. It estimates the corresponding TF, which is written as, oh, it's here. I don't have to write it. It's written as TF being expectation of G Y1 to Ym. So let me just zoom. Yeah, this is the TF. So for the same argument, this estimates, this UN estimates expectation under F of G, right? And that's what? Z, I, Z, J. That's it. A Z, Z1, Z2, I should say. Z1, Z2. That's it. Or maybe using the notation we're more familiar with, I should say, G, Y1, Y2. Yeah, this is more standard because Y1 and Y2 are general notations that follow distribution F. Okay, so this is what's here. And G, Y1, Y2, just go one more step, is just expectation F indicator function y1 plus y2 positive. That's the G function. And now you know expectation of an indicator function is just the probability. So that's why this is the probability under F y1 plus y2 positive. That's it. Okay. Therefore, some asymptotic properties of the sign rank test can also be obtained using the theory of U statistic. This is what I said. Okay, now let's continue from here. In the special case n equals to 1, the V statistic and the U statistic coincide, right? Because when m is 1, there's no issue with sample with replacement, the identical thing. In this case, both UN and VN are asymptotic and normal by central limit theorem, because that's just the average. However, for m greater than 1, the two statistics do not coincide in general. That's why we have U statistic. Furthermore, we may no longer use the central limit theorem to obtain asymptotic normality because the summands, the things in the sum, are not independent, right? Because coming back here, you will, in the sum, there are many xi's appear again and again in these terms, right? So they're not independent. So we need to figure out this dependence issue to get asymptotic distribution. To prove the asymptotic normality of U statistic, we shall use the method sometimes known as the H projection method after its inventor, Houghton. Yeah. So Houghton has been a, how to say, pioneer founder in statistics. So some of his famous work besides this is the Houghton's D for testing independence. That's also under his name. Yeah. H projection method after its inventor, Wesley Houghton. If G at y1 to ym is the kernel function of an expectation function of TF, this is what we define. Suppose x1 to xn is a simple random sample from the distribution F, and let T of F be our parameter of interest, and we denote that as theta. And let UN be the U statistic. We already introduced that. Okay, here's the introduction for the H projection. What does it mean? So typically when we say projection, what do we mean? What is your understanding of it? It means that we go from a high dimensional space to a lower dimensional space, right? That's the projection. And here's the case. So we pick a lower number K. Suppose that K less than M. Suppose that the values Y1 to YK are held constant. So we let Y1 big Y1 fixed at small Y1, big YK fixed at small YK. This may be viewed as projecting the random vector Y1 to Yn onto the M minus K dimensional subspace in Rm given by this. So you see only these dimensions, M minus K dimensions, they can vary. And the first K dimensions are fixed. Okay. And in this case, if we take the conditional expectation, the result will be a function of y1 to yk. So we only take expectations for the latter m minus k dimensions, yeah, which we will denote by gk. To summarize, for k goes from 1 to m, we will define this GK function as expectation functional, but having the first k dimensions fixed. And we're only taking expectations for the latter dimensions. Okay, so you see this is what we're doing. So these are fixed. And now you can make it random, randomize everything. So we randomize y1 to big Y1, small y1 to big Y1, small yk to big Yk. So now these are back to random variables, but we don't take their expectations. That means conditional, right? Putting conditions on them, then they will come back here. So this is the key formula. What's the definition of GK? GK function is for the first k dimensions. That means when we take the expectation, we only take the latter n minus k dimensions random variables, and we are conditional first k random variables. But this two-step thing can get back to your original parameter theta. That is, if you take expectation again for GK on the first k dimensions, then because of a tower rule, right, we have the double expectation. This one is first expectation for the latter n minus k dimensions. Then we take expectation for the first k dimensions. Together, the two-layer expectation will get me back to the parameter, the original expectation. So this is nice because I can get back to the theta. Okay, and why do we want to do this, right? You may think, why do I bother to go through such two-step expectation to get back to the theta? The reason is that we want to use this projection to create some independent cases so we can work with. That's the thing. That's the only reason we want to do that. Yeah. Okay, and we'll see that very soon. And this is very interesting. I will say intellectually very interesting. So this is the mean for expectation of GK at y1 to yk. How about variance? We denote this by sigma k squared. It's the variance under f of GK at y1 to yk. And the importance of what sigma k values, particular sigma 1, is seen in the following theorem, which gives a closed form expression of the variance of U statistics. So I can say that what we're doing here is sort of related to our discussion of the stationary M-dependent sequences. So you need to consider all different variances, right? Decompose the asymptotic variance into terms, and then you put them back. Okay, so yeah, this is it. This is the theorem. Look at it. When n is greater than 2 times m minus 1. What is the m? M is the number of arguments in your expectation functional. Expectation under f of g at y1 to yn, right? That's the m. So basically the complexity of your parameter. And n is your sample size. So you need your sample size to be reasonably large. Yeah. This is the relationship between sample size and the parameter complexity. The variance of a U statistic is in this form. And remember, U statistic has combinations, right? It's like combinatorics and choose M. So it's here. So what we are doing inside here is that K is the K dimensions in your H projection, right? Essentially, you're projecting G to GK by keeping only the first K dimensions. And for the remaining dimensions, you take care of them by expectation. Okay, so under this variance formula, essentially what we're saying is that among the m arguments in your g function, because g has y1 to ym, m dimensions, you first pick k dimensions, right? You consider possibility of picking the k dimensions. And this is what? So from m, you choose k. And from m minus m, you choose m minus k. And these two things are kind of like the binomial formula you have seen before, right? Except that here, or I should say more like hypergeometric formula. Yeah, m choose k, m minus 1 choose m minus k. And this is the sigma k squared, which is the variance here. So we'll see why this is a good way to write this variance. The reason is we can again find a dominant term. So because of this formula, if you expand it, right, by some algebra, if you expand it, and suppose that k goes from 1 to m, all these sigma 1 squared to sigma m squares are all finite, then by expanding this and using asymptotic simplifications, you will see that the dominant terms is only the first term. So m squared times sigma 1 squared is the first term because this is in the order of 1 over n. Other terms are in the order of 1 over n squared, so they are negligible given the first term when n is large. So I think from all these examples, you should be able to see clearly that asymptotics, as we said in the first lecture, is a simplification. It's a simplification of mathematics, right? Use mathematics to simplify the formula. So therefore, you don't have to go through a complicated computation. That's the only reason. And it's necessary, as I said, in the pre-computer age, right? You don't have the computing power. So mathematics is the only tool for you to do these things. But nowadays, as I want to say, it doesn't have to be like this, right? You do have very powerful computers. Yeah, so that's why I know some people are questioning the necessity of learning asymptotics nowadays, but I still feel like it's useful thinking. So the thinking involved in all these ideas is more useful than the than the results themselves, right? It's about how do we decompose the variance and how do we find good approximation, how do we do abstraction, for example, say from actual parameters to the statistical functionals, right? This kind of thinking. And also in many cases, you want to provide a fast solution, right? If you can go with the closed form, it's faster. Okay, so let's look at the proof for this theory. So essentially, in the U statistic, the reason we care about this is U statistic variance, right? We are doing this U statistic multiplied by n over n choose m. So in other words, after you do multiplication, you are only left with these sums. There's no more division of this normalization thing, right, for the possibilities. So in the sum, as I said, you have to pick m things, sample without replacement, right? Sample without replacement, and they have a order from the smallest to largest, and you just assign them to the entries, arguments in your G. That's it. This is the variance. But to derive this variance, the thing I said is not, there are not IID. In the sum, you don't have IID because they may share certain terms. So therefore, what we're doing here is that we consider all covariances of this sum because we know when we open up the sum, variance of a sum, we need to consider each term's variance and their covariances. That's it. So that's why we're considering all pairs of covariances by considering that two terms, two G function terms in the sum overlap by K. They share K random variables from the original sample. They could share 1 or they could share m. When they share m, they are identical. When they are identical, the variance of two identical things is the variance. Okay, so that's why k goes from 1 to m, the overlap from being 1 to m is the all possibilities. Okay, and one more thing, let me see if I want to say this, is this. So if your n is not even 2 times n minus 1, then the problem will be even more challenging because then in this case, you are very likely to sample the identical things, or you cannot even have, how to say, because you need to sample m from n, right? So if n is too small, then you won't have completely unoverlap things, right? So that's the problem. So basically everything become correlated. But now in this case, when n is larger than m, for the covariance part, we only need to consider when the two things overlap by k. Okay, so essentially, it says that we sample k as the common overlap of two 2G terms. And this is just y1 to yk, which is involved in the first term, also y1 to yk involved in the other term. But we know the other entries are non-overlapping. So I just need to sample those from the remaining m minus n. So choose those for the second term. Okay, And that's all possible covariances I would have actually, right? So because this is considering all possible cases where they overlap by K. Yeah, so, and this covariance is something I will show as sigma K squared. This is the thing. Why is that? It's actually from here. So this is a result we haven't, I'm sorry. This is a result. So this is equal to this. This is what we will derive from above. So essentially, to get covariance, we will use the formula that is it's equal to the expectation of product minus product of expectations. Okay, so first get the expectation of the product, which is above. So they overlap the first K, but the remaining M minus K are different. So that's why here the projection makes sense. Since they share the first K, let's put the first K in the condition first. Then in the inner expectation, we are conditioning on the first K. The remaining parts are independent. So we can change expectation of product to product expectation. And here have two conditional expectations. So they're sharing the condition. But in the product, we actually have them separately. And you see, each of them is GK, right? By definition of GK, each of them is GK. And now I have expectation of GK squared. I go back to the fact that it's equal to the variance plus the mean squared. And variance is defined by definition sigma K squared. That's what the notation definition. Mean is theta, so theta squared. Okay, so that's why we have this expectation of the product. And putting this inside the covariance, then we know it's the what we just derived here from above minus product of expectation. Each is theta squared. So that's why we show that it's sigma K squared. That's it. So nothing beyond calculation, but you can see that introduction of the projection makes things easier. Okay, and so this is our formula for the variance of U statistic multiplied by n choose m. That's it. So we get it here. And then for the remaining steps, we just need to say that just algebra. You just expand things and to get the order for each term in terms of m. And we will say that the dominant term is this. So that means even though in the U statistic, you do have terms that may overlap more, but what you only care about is the variance of G1. Okay, G1 means what? G1, if you go back to the definition of G function, G1 is you only have Y1 in the condition, and you take the expectation of everything else, right? So in this case, you are reducing G from m-dimensional to one-dimensional. G1 is one-dimensional. And you can imagine for G1, everything has its own thing. Then it's like the central limit theorem case. Okay, so I'm just jumping a lot of, I jump a lot of the details, but just want to give the intuition that if you use asymptotics, which means that we can make the U statistics variance, asymptotic variance, much simpler. And as you know that when we derive the asymptotics, we multiply the statistic on the left-hand side by what? By root n. By root n, it means that you can cancel out this 1 over n right here. And this is the only term, m squared times sigma squared is the only term left in your asymptotic variance. And other terms will go to 0. Okay, I already said that. This theorem shows that the variance of root n un tends to m squared sigma squared. And indeed, we may well wonder whether it is true that un as an unbiased estimator for theta, this thing, root n times un minus theta, is asymptotic normal with limiting variance. That's the goal, to show that. It is the goal of the Hoeffding-H projection method to prove exactly that fact. We will derive the asymptotic normality of un in a sequence of steps. The basic idea will be to show that un minus theta has the same limiting distribution as this un tilde. So we are not working on this asymptotic distribution directly, but we use a surrogate, un tilde. So essentially, we are basically taking un minus theta, the target, by taking conditional expectation on each of xi. And xi is an x1 to xn are IID from distribution F. Okay. As I said, here we want to leverage central limit theorem. So by conditioning on each xi, then these conditional expectations, they are IID. Okay, so these are IID, right? Because condition expectation is a random variable just because of its condition. Okay, since x1 to xn are IID, then these are IID. Okay. For projections. Okay, let's move here. Now, we'll say the asymptotic distribution of un tilde follows the central limit theorem. I just said that because un tilde is the sum of IID random variables. So let's first derive the entries in this. So in the un tilde, let's first get each entry here, each term in the sum. So first we say that for all I from 1 to n, expectation under f of un minus theta given xi can be shown as the g1 xi minus theta times m over n. Again, n is the number of entries in the g function, and n is the sample size. Theta is the parameter of interest. G1 is the h projection by fixing the first entry. So you can expand un going back to its definition. So essentially, un is 1 over n choose m times a sequence of sum, right, of g at xi1 to xim. So what we're doing here is that we move the expectation inside the sum. We move the expectation in here, and it's a conditional expectation given xi. So now let's discuss the possibilities of the relationship between xi and I and this I1 to IM. If I is one of the I1 to IM, what happens? That's the definition of H projection. If I is one of them, it's just conditional on one of them, right? And taking expectation of the rest. That's exactly the definition of G1. Yeah, G1 at xi minus theta. But if xi is not one of them, then the condition is independent of the random variables before it, then this conditional expectation will be equal to the unconditional expectation. And this is the definition of theta as expectation, right? So that's why we get 0. So you see that the number of ways to choose I1 to IM so that I is among them is how many? N minus 1 choose N minus 1. Because we fix 1 as I, then we need to only choose the remaining N minus 1. So that's why we consider all these non-zero possibilities here, and we do the cancellation. And that's it. Okay, that's how we simplify this term. So essentially, I think for this part, we're using mostly combinatorics to help us do simplification. So this is the result. And this will make it much easier to derive the asymptotics of un tilde. Remember, un tilde on the previous page is the sum I from 1 to n. Expectation of f un minus theta xi. Right, this is the un tilde. So now we know that we simplify it, then it's basically n over n out, I from 1 to n, g1 xi minus theta. That's it. Okay. So next step, how do we derive asymptotics for u and tilde? This is the lemma. You can see that if sigma 1 square, which is the variance of G1, is finite, then root n times u and tilde converges in law to normal distribution with mean 0 and the asymptotic variance we desire, n squared times sigma squared. So this is a result by applying central limit theorem to this, right? Because it's a sum of IIDs, G1 xi, right? Xi's are IID. Yeah. And since this here, m time, because you see by multiplying root n here, I can have cancellation of n on right hand side. So essentially, this is saying that m, you need to get the variance of m times G1 xi, and that is mean 0, that has variance m squared times sigma 1 squared, because sigma squared is the variance of G1. And the expectation of G1 x1 is theta. So I just write here. So expectation G1 xi is theta. That's what we previously showed. Variance G1 xi sigma 1 squared. That's it. So we're applying that to get this lemma result. Okay. And I will say that this part is trying to get the basically covariance of u n tilde and u n minus theta. So remember that we're trying to use the asymptotics of u n tilde, right? So we already have that. So given this, what can we say about asymptotic distribution of u n minus theta? Okay, so to answer this question, this lemma is trying to give us some coupling, right? How these two things are joined. We do that. And I will say this is a technical lemma. We need that for going from here to here. Another technical lemma is this one. We want to say that their difference is going down to 0 in probability. Yeah. So with this and these two, with all these lemmas, and basically I would say that this lemma result will be used in this one. And with this one, then finally we get to the asymptotics of the U statistic. This is the final result we desire. So the introduction of the U and tilde is just for proof. We need to derive the asymptotic distribution. Yeah. And it's not easy because in the UN, in the sum, the terms are not independent. But we are saying that their dependence is dominated by the ones that overlap by just one random variable. That's the thing. So it's like in M-dependent sequences, right? The dependence doesn't dominate. Yeah, we just need to account for the covariances among the M dependents. That's it. Okay. Now maybe I can show you some examples. I think that will make things more concrete, right? So we have talked about this abstract thing. Again, M is the number of arguments in G. Sigma 1 squared is the variance of G1. That's the H projection by fixing the first entry. So now let's look at this example 3.
Professor, I have to go.
Sure.
Sorry.
No problem. Thank you. Thank you. I'll see you next time.
Yeah.
See you on it. Yeah. Okay, so example 3. Consider expectation function node defined by the kernel function with two arguments, g, y1, y2 equals to y1 minus y2 squared over 2. We obtain this expectation function node, tf, as expectation of f at f of g, y1 and y2. So by plugging this g here, essentially this is just 1/2, which expand this g, right? Expectation of y1 squared plus y2 squared minus 2 times y1, y2. And because y1 and y2 are IID from F, we can combine the two copies of square expectation, right? And also and we can have expectation of y1, y2 equals to expectation of y1 times expectation of y2. So we simplify it this way. And you see it's exactly variance, right? Because y1, y2 are just copies of y. So you see variance can be defined as expectation functional with m equals to 2. And given a simple random sample, x1 to xm from F, let us derive the asymptotic distribution of the associated U statistic. So we just follow that definition. So UN is 1 over n choose 2, I less than j. G applied to xi and xj. Yeah, we simplify it, that's it. Where we have to use the fact that g, xi, xj is 0 whenever I equals to j. This is because of the definition of g here. When they're equal, then it's 0. Okay, so then in this case, we use the g function, we get a U statistic. That's it, right? We just sample everything, I and j as two non-identical pairs. And then we just expand it, that's it. And we also use the fact that x bar square, if you expect this is average, you put in the average formula, it's actually turned out to be this. So you will use this to introduce x and bar in here. And by simplification, you will finally see the U statistic is just the unbiased sample variance we're familiar with. So in this example, nothing special. We're just showing that U statistics generalizes the unbiased sample variance, and unbiased sample variance is a special case. That's it. Okay. And you can see that although we have already derived the asymptotic distribution of the biased version of sample variance, so we previously derived this 1 over n version. Yeah, biased version, that's what we mean. Previous lecture. Here we can check that by using the general U statistic theory, asymptotic theory, we will get the same asymptotic distribution as before. Remember, when we derive this, we are just using what? We are using central limit theorem and delta method. That's what we're doing, yeah. Then now we're using the U statistic result. And here, remember the result is n squared sigma 1 squared. Here m equals 2, right? 2 squared is 4. And then we just need sigma 1 squared. So we'll show that is this. So it means to find sigma 1 squared because we know 4 already. To this end, we must define the projection, G1y. So let U be the mu, be the mean, sigma squared be the variance. We obtain G1y as the expectation of G, fixing the one argument, first argument, and take expectation for the second argument. So expectation for the second argument is y2. And by doing so, you can see that we introduce mu as expectation of y2 and sigma squared plus mu squared as expectation of y2 squared. Therefore, the sigma 1 squared is the variance of this g1y. You put it back in. So y becomes y, the big Y random variable. And here, you just do that and you can find that. Oh, and also one thing to say is that when you calculate the variance, you can drop the constant. The constant doesn't affect the variance. So essentially, you can show that this is the variance of sigma 1 squared. And this is exactly what we have in the previous lecture. So the 4 and 1/4 will get canceled. Yeah. So it's just application to show that U statistic generalizes the things we talked about, like the unbiased sample variance. Okay, so, and something remaining here is the multi-sample use statistic. So I feel like this is the part I can potentially skip because it will actually be a little more complicated, but not more complicated conceptually or more complicated notation wise. Like, let me just show you this. So essentially, if you have S samples in total, right, in your use statistic, you need to consider sample without replacement from each sample. Yeah. So, and this is something you will need when your statistic involves more than one sample. And for example, like if we're doing this Wilcoxon rank sum test, yeah. But actually, we can talk about this a little bit just for your fun, but I think we can be quick in terms of going through the notations. So probably we can just pause here for the first lecture, and then we can take a short break and then resume.